Okay, so where we left off was we were trying to finish up drawing this mechanism where I was missing an methyl group here, and then we have our alkoxide, and we have our sodium cation, like that. And of course, we liberate hydrogen gas. All right, there we go. So those are two ways to make an alkoxide. One is to treat it with an alkali metal, and the other way is to use sodium hydride. Somebody asked me, is there a reason why you would use one over the other? I would say it would be substrate specific. Sometimes you might try both and you figure out which one gives you the best yield, and you would probably go with that. The only thing I can tell you, Tiana, is from personal experience, I would avoid any reaction where I have to use pure sodium, because sodium is highly reactive and it's a pain in the neck to work with. It has to be stored in oil so that it doesn't get oxidized in the air. Whereas sodium hydride, on the other hand, that's a white solid that's not easy to manipulate because it's stored in mineral oil, but I would say it's much easier to use. So I would go with the sodium hydride. That would be my first choice. All right, let's take a look at question 12.6. This one kind of has to do with areo. It says identify for the following pairs of alcohols. Identify the one that's more acidic and explain your choice. Well, after I said that, the very first example here doesn't involve areo, does it? Can anybody tell me which one of these would be more acidic? I'll call this one A and I'll call this one B. Which one of these would be more acidic? It's going to be A, right? More acidic. And then we'll put here solvation effects. Solvation effects. So A is a primary alcohol where B is a tertiary. Thanks, Huang. Thanks, Audrey. Perfect. If I look at B, if I call this one, I'll call this one, oops, where's my red pen? I'll call this one C and I'll call this one D. Which one would be more acidic? It would be C, right? And what would be the main reason? You could use a one-word answer. Induction, absolutely. Induction. I'll call these ones E and F. What about this one? Which one is more acidic, E or F? It's going to be F because of resonance, right? So resonance, right? If we draw all the resonance contributors for both of these, we see that F has one more resonance contributor, right? If you draw the alkoxide, or sorry, the phenoxide, I should say, like this, and then we have our methyl ketone, you can push arrows where you put the negative charge here, and then here, and then here, and then push it all the way up to the oxygen, like that. And then for the last two, call this G and H, we'll say it's going to be H, and we'll say that's due to resonance. Resonance, right? A phenol is much more acidic than terbutanol. All right, so let's move into section 12.3. The good news is section 12.3 is review. Okay, these are all things that you learned back in Organic Chemistry 1. So everything in here is Chemistry 3101 is section 12.3. These are all reactions that you saw back in Organic Chemistry 1. So the first way that you would have learned to make an alcohol would be with dilute sulfuric acid. And if you just put, you know, H3O plus, that works for me. Any kind of strong acid in water is going to give you a Markovnikov addition of water across a double bond. So we call that an acid catalyzed hydration. If you want to do an acid, or sorry, if you want to add water across a double bond in a Markovnikov fashion, but you want to avoid carbocation rearrangements, in that case, you use oxymercuration, demercuration. And if we want to do an anti-Markovnikov addition, in that case, we use hydroboration oxidation. And so these are all reactions that you should know frontwards and backwards, not only from chapter, chapter 8, but also from chapter 11 that we just went over. And so let's take a look at one more. Oh, I think that's it. Let's try some of these questions here. Some of these are going to be more challenging than others. You have to go back into chapter 7 to answer a few of these. So if you're reviewing this at home, I would say this would fall under the umbrella of chapter 7 and chapter 8 is where you would find the information for this. So the first one says you want to take a tertiary alkyl halide. So remember, look deep into my eyes. This is a tertiary alkyl halide, and we want to make a tertiary alcohol. First of all, could anybody answer me, would this be an SN2 or an SN1 reaction mechanism? What do you think? Would this be SN2 or SN1 if I'm starting with a tertiary alkyl halide? It's SN1, isn't it, right? This is an SN1 reaction. And so this reaction is actually a solvolysis reaction. So solvolysis reaction. And so all you need to do this reaction is water. Just put it in water, the leaving group's going to leave, then water is going to come in as a nucleophile. Whereas the next one, since we have a primary alkyl halide, and we're making a primary alcohol, this is going to be formed by an SN2. Could anybody tell me what reagent I would use for an SN2 here? What would be a good reagent for an SN2? There's only one possibility to make an alcohol from an alkyl bromide, or a primary alkyl bromide. It's sodium hydroxide, right? Thanks, Avishi. So it's sodium hydroxide. Let's see here. What about the next one? C. Would that be Markovnikov or anti-Markovnikov addition in C? It's Markovnikov. Yes, absolutely. You guys are very quick. So for that one, we just need H3O plus. So this is Markovnikov, and there's no possibility for a rearrangement to occur. So we don't have to worry about that one. The next one is an anti-Markovnikov addition. So for that, you need hydroboration oxidation. So we'll put BH3 and THF, followed by peroxides, sodium hydroxide. And the last one is a Markovnikov addition, but would this be susceptible to a rearrangement, the last one? If you were to protonate E, could it do a rearrangement? So let's see, if we were to do an acid catalyzed addition across that double bond, you would end up with this carbocation. Can this undergo a rearrangement? Absolutely it can, right? This can undergo a rearrangement to give you this compound, right? This tertiary carbocation from a secondary. So we want to avoid this rearrangement, and so we have to use oxymercuration demercuration. So our first step is going to be mercuric acetate in water, and then in the second step we use sodium borohydride, and that's oxymercuration. Oxymercuration demercuration. So we want to avoid methyl shift, right? So that's why we use these conditions. Okay, now we're going to get into reduction. So reduction of a carbonyl. So how do we reduce a carbonyl? So let's get into that in detail. Of oxidation state of carbon to you, and don't worry about it. It's very straightforward. I wouldn't say it's the easiest thing that you'll ever see in your life, but it's relatively straightforward. So it says, another method to prepare an alcohol is the reduction of a carbonyl. So what's a carbonyl? A carbonyl is when we have a carbon with a double bond to oxygen. And thus, let's say we took something like a ketone, like acetone, and we converted that into a secondary alcohol. That would be considered a reduction. Now, the way that I teach oxidation and reduction in nursing chemistry is we say that a reduction is gaining hydrogens or losing oxygens, and then oxidation is gaining oxygen or losing hydrogens, or some combination of those. However, in this class, what we're going to do is we're going to look at actually evaluating the oxidation state of the carbon. Somebody asked me, is there a difference between a carboxyl and a carbonyl? The answer is absolutely, right? The carbon with a double bond to oxygen, that's a carbonyl. And a carboxyl group is when we have this. So this, oops, can't see very well here. There we go. That would be a carboxyl group that's found in the carboxylic acid. So carboxyl group. All right, there we go. So now we're going to take a look at oxidation state, and we're going to compare it to formal charge, because they're both methods of electron bookkeeping. They're both extreme methods. They're both very different. So just to review, going back to your general chemistry 1 days, if you were evaluating the formal charge of this carbon, the formal charge of that carbon is 0. And the way that you calculated formal charge is that when we do a formal charge, we break the bonds homolytically. So we assume that in each bond, one atom gets one electron and the other atom gets the other electron. And if you're thinking, wasn't it something to do with sticks and dots, Mr. Dion? Yeah, that's the method I teach my students, is that formal charge is equal to the number of valence electrons, subtract the number of sticks, subtract the number of dots. Okay, that's what I teach my students. So if we take a look at methanol, carbon has 4 valence electrons. Subtract 1, 2, 3, 4 sticks. There's no lone pair, so there's no dots. 4 minus 4 gives you 0. Okay, so I'll just pencil that in here. So on the carbon, you'd say 4 minus 4 equals 0. However, the oxidation state of this carbon is actually, it's actually -2. So if you're wondering, well, where do I get the -2 from? Well, the way that we do it when we're calculating oxidation state is that we break the bonds heterolytically. So what does that mean? It means we don't split up the electrons evenly. We give both electrons from the bond to the more electronegative element. So if we zoom in on methanol, there are 4 bonds. If you look at the bond between the carbon and the oxygen, oxygen is more electronegative. If you look at the bonds between carbon and hydrogen, carbon is more electronegative. And so for the 3 bonds in blue, carbon takes all of those electrons, all 6 of them. And for the bond between the carbon and the oxygen gets the pair of electrons. And so to calculate the oxidation state, what we do is something similar. We say 4 valence electrons for the carbon, but then we subtract the number of dots. How many dots are there? There's 6. And so we end up with an oxidation state for the carbon in methanol, which is -2. So we have a -2 oxidation state. Again, its formal charge is 0, but its oxidation state is -2. So now you remember that going back to your Gen Chem 1 days, oxidation is losing electrons and reduction is gaining electrons, right? The old oil rig mnemonic or axiom. So if we go back to our methanol, we see that it's -2. If you were to convert methanol to formaldehyde, that would be considered an oxidation. Why? Because the oxidation number is going from -2 to 0, you're losing electrons. If you were to go from formaldehyde to methanol, you'd consider that to be a reduction because you're going from 0 to -2, and thus you're gaining electrons. Give me a thumbs up if you're even like 60% of the way with me on the idea of oxidation state. Any questions about that? We're going to take a look at some examples, of course. All right, so let's just try one more. Let's see if we could calculate the oxidation state of the carbon in formic acid. So look at all the bonds. So let's draw it out here. We've got the carbon and the oxygen. Who's more electronegative, carbon or oxygen? What's more electronegative, carbon or oxygen? Not a trick question. It's oxygen, right? So oxygen already has a lone pair, and you're going to take both electrons from those 2 bonds, 1, 2, 3, 4, and they're all going to go on the oxygen. Now we have this bond here between carbon and oxygen. We just told me that oxygen is more electronegative, so it's going to take the 2 electrons. So if I look at the bond between carbon and hydrogen, carbon is more electronegative. So carbon takes 2 electrons, and the hydrogen has no electrons. So what I'm looking at is everything in here. Okay, I'm kind of working with limited space. So now when I calculate the oxidation state, I say 4 valence electrons for carbon, subtract 2, and that gives me +2, like that. And there you have it, my friends. That's how you calculate oxidation state. Nothing more than that. And so we can evaluate oxidation state and say if electrons were gained, we're doing a reduction, and if they're lost, we're having an oxidation process taking place. So if we convert a carbonyl to an alcohol, this is a reduction. Why? Because we're going from a carbon that has an oxidation state of +2 to a carbon that has an oxidation state of 0, right? So again, we're gaining electrons, right? Reduction is gaining electrons. And there you have it, my friends. So I told you could also look at it from a simpler point of view and say, well, what atoms are you gaining? You're gaining 2 hydrogens, right? You're gaining this hydrogen and this hydrogen. And since you're gaining 2 hydrogens, that's also considered, or another way to evaluate it, as a reduction. So how do we actually reduce a carbonyl group? Well, here we have cyclopentanone, which is a ketone, and we're reducing that ketone to cyclohexanol, an alcohol. The way that we do that is using catalytic hydrogenation. And you're probably looking at this and saying, wait a second, this is the same thing that I saw with alkenes. I could take an alkene and treat it with hydrogen, palladium, platinum, or nickel, and I would get the addition of the two hydrogen atoms. Well, we're doing the exact same thing here, right? We're adding 2 hydrogen atoms across that double bond. What I have shown here in this picture is 3 balloons that are filled with hydrogen gas. So this is hydrogen gas in each one of these balloons. And then the solution in the bottom that's got kind of a dark color to it, that's the palladium or platinum catalyst being stirred around with the ketone in there. The only thing about this method, using catalytic hydrogenation, it works. However, the caveat, I would say, is that hydrogen is explosive, so we generally frown upon explosions in the lab. And I'd say another thing, and I don't have a lot of space here, but I'll just expand this. Explore the space, Gene, right? Anyhow, I'd say if you have, let's say you had this, a cyclopentanone with a double bond in it, right? And then if you treated this with hydrogen and nickel, it's going to reduce everything. So you'd reduce the double bond and you'd reduce the carbonyl. So you can't selectively reduce one over the other. So that's kind of a pitfall of using hydrogenation of a carbonyl, but it does work. All right, the next possibility is to use sodium borohydride. And this is actually a reagent we let students use in the undergraduate lab. Usually in organic 2, I get my students to do one reduction where they take sodium borohydride and they dump it in a flask. So it's actually pretty safe to use. And you can see it's just a plain old white solid here. There's nothing really special about it. This is just your bottle of NaBH4. And sodium borohydride is a common reducing reagent for aldehydes and ketones. So what it does is it adds 2 hydrogens across the double bond. So of course we have this one, and then we added another one here. So we would convert a ketone to a secondary alcohol. And let's imagine we had an aldehyde like this. If you did the same thing, you'd end up with a primary alcohol like that. So again, ketone to secondary alcohol, aldehyde will give you a primary alcohol. Well, something that we haven't looked at a lot of yet this semester, this summer semester, are mechanisms. And I do expect you to know the mechanism of this reaction. And it's shown right here. So what happens is, first you have to be able to draw the Lewis structure of sodium borohydride. So we have the sodium cation, and then we have the borohydride anion here. Okay, and you can see it drawn right here. So what happens is one of the hydrogens is delivered to the carbonyl carbon as a hydride. And when that happens, it does a nucleophilic attack, and we end up with an alkoxide. So you can see here, this is an alkoxide. And then what happens, since we do the reaction in a protic solvent like ethanol or methanol or water, as I have shown on the previous slide, and I forgot to mention it, we can use ethanol or methanol or water. Then in the second step, we remove a proton from that solvent. Here they're showing methanol as the solvent and the proton being removed from it. Now, something that you might find interesting, and maybe not depending on the students, if you do a Google search of this mechanism, you might actually find another version of this mechanism that is more complex than this one, where it shows the sodium being involved as a Lewis acid and all these things. I'm not going to ask you anything about that. This is the mechanism that you need to know for our class, okay? And it would apply for the ACS final or an MCAT as well. This is the mechanism you need to know. Step number 1, sodium borohydride. Step number 2, your solvent donates a proton. You know, going back to the reducing agents, you know, if we look at a ketone that's unsymmetrical, in that case, you know, it's trigonal planar, the carbon in the carbonyl, right? This is sp2 hybridized, and therefore it is trigonal planar. And so if it's planar, that means that the nucleophile, the hydride, can come in and attack from either face of the molecule. There is no discernment whatsoever. And so in that case, we end up with a pair of enantiomers. So enantiomers. Like that. There's nothing we can do about that. So again, if you're using an unsymmetrical ketone, you're going to get a pair of stereoisomers. All right, next. So now we've covered hydrogenation of a carbonyl. We've covered reduction with sodium borohydride. So just to recap, the first one was hydrogenation with nickel, palladium, or platinum. Number 2 was sodium borohydride with in water or methanol or ethanol. I'll just put water. And now we're on to number 3. And number 3, this is the strongest of all the reducing agents that we're going to look at today. And we call this lithium aluminum hydride. So this is a very strong reducing agent. You can even see it comes in this hermetically sealed can or whatever, and that's to avoid it getting in contact with the air. And the acronym that we use for lithium aluminum hydride is LAH. Sometimes I use LiAlH4 like that, which is just the molecular formula of the compound. But for lithium aluminum hydride, its Lewis structure looks like this. So we have the lithium cation, and then we have the aluminum hydride ion like this. And if you're wondering, well, hold on, this is kind of reminiscent of the borohydride. Does that mean that this can deliver a hydrogen as a nucleophile? And the answer is absolutely. Absolutely. The difference is this, is that lithium aluminum hydride is so reactive that it can actually cause a fire if it comes into contact with water. And so that's why we have to do this reaction is 2 steps. First step, lithium aluminum hydride. Second step is water. Right? So if we go up here, we'll put step 1 is LaH. Step 2 is H2O. Notice that for sodium borohydride, we combine the water and the sodium borohydride, but with lithium aluminum hydride, we cannot do that. So, yeah, there we go. It's a 2-step process when we use lithium aluminum hydride. So we abbreviate that LAH. All right, so here's the comparison of the borohydride ion and the aluminum hydride ion. You can see they're very similar in their structure. And if you're wondering why is one more reactive than the other, our textbook actually doesn't go into any detail about that whatsoever, but it is based on the electronegativities of aluminum, which is about 1.6, and boron, which is around 2. Also, lithium is a stronger Lewis acid than sodium, and that renders the carbonyl more electrophilic. I'm not going to ask you anything about that. What you need to know in this class is that lithium aluminum hydride is much more reactive than sodium borohydride. Nothing more than that. Very reactive. So on top of that, like I mentioned before, you do need to know the mechanism. This is my thing, is usually when there's a mechanism you need to know. I put a little red star by that. So you need to know the mechanism. Step 1, the aluminum hydride ion delivers the hydride as a nucleophile. You form your alkoxide, and then in the second step, you treat it with water, and that does the protonation, and you end up with the alcohol. All righty. So let's take a little kind of snapshot review of what we've covered so far. The first thing is that we have our hydride ion that can be delivered in the form of sodium borohydride or lithium aluminum hydride. Remember that lithium aluminum hydride is a much stronger reducing agent. It's actually able to reduce more functional groups than sodium borohydride can. Sodium borohydride can only reduce aldehydes and ketones, whereas lithium aluminum hydride can reduce aldehydes, ketones, esters, and carboxylic acids. That's another day, so we're not going to worry about that right now. Whereas hydrogenation is a good reduction method, but it can also reduce double bonds, whereas sodium borohydride and lithium aluminum hydride don't do that. All right, so let's see here. What else do we have? The reactivity of that hydride ion in the borohydride or the lithium aluminum hydride, it can be mitigated. So in other words, there's all kinds of reagents out there that we can use that will decrease the reactivity or increase it. And so there's a whole variety of different R groups that you can put on your aluminum or borohydride in order to cause it to be selectively reactive. And that's something that we'll see much, much later on in the course. Now, you remember that on the last slide, I mentioned that lithium aluminum hydride can also reduce carboxylic acids and esters. So let me show you what that looks like. The way that we do that is that instead of just putting LAH, we have to use an excess of LAH to reduce a carboxylic acid or an ester. And there's a good reason for that. You need more than one equivalent of the hydride ion to do the reduction. So in the first step, we use lithium aluminum hydride in excess, and then we put in water. And if you were to even put in here, you could even put H3O plus, and I would accept that. Either way, it's going to work. Usually you would use a buffer. Anyway, so there you go. So if we reduce a carboxylic acid or an ester, we end up with a primary alcohol. And when you reduce an ester, you end up with two primary alcohols, right? You end up with the one that comes from the carbonyl group, right? You end up with this part. And then you also end up with part that comes from the alkoxy group that gets lost in the reaction. And there we go. So here's the mechanism of the reduction of an ester with excess lithium aluminum hydride. This is a mechanism you definitely want to know. Let's take a look here. It's not meant to be, mega complicated. The first step is just a nucleophilic attack. But once you make the alkoxide is going to eject methoxide as a leaving group. And you might think, well, that's not the best leaving group in the universe. Well, there's a good reason why that gets lost. It's because it says here the methoxide is not a good leaving group. So that means methoxide that's being lost here, it's not a good leaving group. But because the high energy intermediate becomes a stable aldehyde. So we end up forming an aldehyde in the process. And then the aldehyde gets reduced by the second equivalent of lithium aluminum hydride. And that gives you your primary alcohol after protonation. So again, it kind of goes like this. This is your first molecule of lithium aluminum hydride. Then you form an aldehyde. So here's your aldehyde. Then you have your second molecule, ion of lithium aluminum hydride. And then in the third step, we protonate it with water. And you can see here that they used H3O plus instead of water. Either one is perfectly acceptable in my mind. So with that in mind, let's see if we can draw a mechanism for the reduction of an aldehyde with lithium aluminum hydride. So we'll start out by drawing the aluminum hydride ion. So we'll start by drawing the Lewis structure of that. I'm going to leave the lithium out of it because it's a spectator ion. It's not really that pertinent. So we're going to have our nucleophilic attack, and we're going to form our alkoxide. And so what's that going to look like? We've got a methyl group here, and then we've got the alkoxide here. Look, if I highlight this hydrogen in green, right, so I already have one hydrogen here. The second hydrogen is the one that came from the lithium aluminum hydride. And then in the next step, I'm going to protonate it with water. So I'm going to put a water molecule here. And if you put H3O plus, that's totally fine too. Put in my lone pairs on my alkoxide. That's going to grab a proton from water. And I end up with a primary alcohol. So I end up with this here. There's a primary alcohol. So what I'd like to do now is take another short break. I'll give you a chance to try the mechanism with sodium borohydride. Then we'll come back and take a look at that. And then we're going to get into diols. And then we're going to get into a Nobel Prize winning reaction known as the Grignard reaction. It's one of the last reactions that we get our students to do in the organic 2 lab because it's a pretty challenging reaction, doable, but challenging. And also it's a really cool reaction because somebody won a Nobel Prize for it.